Hello, good morning, good afternoon, good evening, wherever you are. Welcome to the SNIA Ethernet Storage Forum webcast, ROCE versus iWARP, part of our Great Storage Debate series. So we're happy to bring in this webcast. We've got two great presenters here, and we've got an interesting topic, debating what is the best, or perhaps what are the most popular or what are the differences between these RDMA solutions. So we have presenting today Tim Lustich of Mellanox and Fred Zhang of Intel. I am John Kim, your humble host. I am chair, also from Mellanox, and I am the chair of the SNIA Ethernet Storage Forum, and happy to host this webcast today. Before we get started, we have a couple of logistical issues and slides to cover. So first, I want to remind you about SNIA. If you're not familiar with us, SNIA is a group very active in the storage and networking industry. We have over 170 leading organizations who are part of SNIA, over 3,500 active contributing members, and over 50,000 total IT end users, storage professionals, vendors, resellers, and other partners related to the IT industry who participate in SNIA. You can learn more about SNIA's work if you go to snia.org/technical, and you can follow us on Twitter with @SNIA. You can specifically follow the SNIA Ethernet Storage Forum on Twitter at @SNIAESF. Our standard legal notice and disclaimer: this material is copyrighted by SNIA unless otherwise noted. Member companies and individual members of SNIA may use this material in presentations and in literature under the following conditions: that any slide or slides used must be reproduced in their entirety without modification, and that SNIA must be acknowledged as the source of the material. This is a SNIA project. Neither of the authors or any of the presenters are attorneys, and nothing in this presentation is intended to be or should be construed as legal advice or the opinion of counsel. If you need legal advice, please consult your attorney. And finally, some of the information, or most of the information herein, represents the authors and presenters' personal opinions and current understandings of the relevant issues involved. Therefore, SNIA does not assume the liability or responsibility for any damages arising from your use of this information. No warranties expressed or implied. Please keep that in mind. Now that we've gotten the legalese out of the way, what are we going to present today? So first, I will cover a brief introduction and talk about what is RDMA as an introduction to this. And then Tim and Fred will cover ROCE and iWARP, which are the two most popular, the only two solutions for RDMA on Ethernet today. And then we'll cover the similarities and differences between the two, talk about some use cases for ROCE and iWARP, and then we'll take questions from the audience and maybe have a challenge discussion talking about how do they compare in terms of performance and manageability, and basically, security costs and other comparisons, which I'm sure you'll be interested to ask about. So as we go forward, please feel free to ask questions online. We will take all the questions we can. If there isn't enough time to take all the questions, then we will answer any remaining questions in an FAQ, which we publish on our website, usually about a week or week and a half after this webcast. So please feel free to ask away. Bring all your questions. So the first part of our introduction is, what is RDMA? Well, of course, it stands for Remote Direct Memory Access. So it's the ability to do a direct memory access from the memory of one node into the memory of another node without involving the operating system or the CPU, or without bothering the CPU of either system. These nodes could be servers, they could be storage, they could be GPU nodes for artificial intelligence and machine learning. Generally, RDMA is server to server or server to storage, and in some cases, storage to storage if you have like a storage cluster. RDMA is performed by the network adapter, so it's offloaded to the network adapter hardware, and therefore no work needs to be done by the CPU. You don't have to copy the data and make extra copies in the caches or at the kernel level, and you don't have so many context switches that would slow down or bother the CPU. So while the CPUs are still involved maybe in processing the data or figuring out what needs to be transferred, the actual data transfer and the networking are offloaded to the networking adapters. This means you get higher throughput, lower latency, and reduced CPU utilization, leaving more of the CPU power to do important things like run the application or run the hypervisor and analyze the data. So that's the advantage of RDMA. Now, to actually do RDMA, you need some way to transport the data because it's done, the R means remote. It goes over the network. The most popular storage use case of RDMA is actually for block storage, but there are other use cases. And so let's look first at that. So with block storage, the most popular block storage protocol is, of course, SCSI. And SCSI traditionally runs on top of TCP over IP. So that's usually what I'm sorry, take that back. SCSI can run on top of fiber channel, on top of IP, on top of other protocols. Local SCSI can be on top of PCIe or SAS. But when we talk about over a network, SCSI usually means over a storage networking protocol, and iSCSI usually means SCSI over TCP/IP. Now, you can use other protocols for networking storage. So SMB, SMB3 is a protocol that started on Windows, though it's now also supported by Linux and other operating systems. And there's a version of it that supports RDMA called SMB Direct. And then NFS also has a version which can support RDMA called NFS over RDMA. And then if you look here, Storage Spaces Direct is a Windows-specific solution. It's sort of a hyper-converged and storage solution where the storage is distributed across servers and shared with this protocol that's based on SMB Direct, and it's called Storage Spaces Direct. So that also takes advantage of RDMA. Now, how do I transport RDMA? So I've got this very efficient, performance-enhancing, CPU-saving way to talk from one server to another or storage to a server, but I have to transport it somehow. And so the three ways you can do RDMA today over the network are InfiniBand, ROCE, and iWARP. Now, most of the implementations, the majority of the RDMA out there is in fact over Ethernet, so it's using either ROCE or iWARP, and that's what we're focusing on today. In terms of a standard, ROCE is standardized by the IBTA, the InfiniBand Trade Association. iWARP is standardized by the IETF, Internet Engineering Task Force. So some of the RFCs, or requests for comments, which cover iWARP are listed here, and as well as the availability dates, ROCE first becoming available in 2003, and iWARP first becoming available in 2007. And if you look at this stack, we see that if I want to transport a storage protocol over ROCE or iWARP over RDMA, first I use TCP, then on the left, SCSI would go over iSCSI, which then goes over TCP and IP, and then from the initiator to the target, and then back. But if I use RDMA, then it goes to RDMA over specific transport, which in this case would be iWARP or ROCE, and then it's on the other side of the network. It's translated back into RDMA calls and then back into a SCSI protocol. So that's an example of how, say, iSCSI RDMA would operate over iWARP or ROCE. And it works similarly, thank you, for NVMe over fabrics as well. Okay, we have a couple of questions. I'll answer. We'll get to those in a minute. One is, can we get a copy of the charts? The slides will be made available as they are for all SNIA webcasts as PDF files on the website, and you will be able to download them. So you'll be able to watch this as a replay in BrightTalk or download the slides from the SNIA website. So there's a brief question, what is SMB Direct? So SMB Direct is the special high-performance version of the SMB3 protocol, which was led by Microsoft, though it's also supported in Linux. And SMB Direct is a version of SMB3 which uses RDMA and multi-channel or multiple connections to get the maximum performance. So with that said, let me hand it over to Tim Lustich to talk about ROCE.
Thanks, John. Forward this real quick. So RDMA over Converged Ethernet, or as it's pronounced, ROCE, it provides a seamless, low-overhead, scalable way to solve the TCP/IP I/O bandwidth issues with minimal infrastructure and cost. So if we look at what ROCE is doing, it addresses three key limitations, namely overhead created by data copies between user applications and kernel memory, and the latencies that are introduced by the TCP/IP protocol. And finally, the last thing it resolves is CPU utilization. It bypasses the CPU, so it can free up those CPU cores to do other application processing, which, when you put all these three together, it affects the way that data is transferred, and RDMA will will help make it more scalable and overcome those bottleneck issues. So TCP/IP or TCP is very inefficient for high-performance network transports. And as we're seeing right now, network speeds are increasing. We're seeing more and more CPU cores that are being devoted to handling, are needed to be devoted to handle network traffic to handle these TCP/IP related data copies and interrupts. ROCE will go ahead and bypass that, the entire system software stack for TCP, and it does the processing of these within the adapter's silicon to handled by the adapter itself. So it bypasses the kernel, application issues, and commands directly to the NIC without having to execute any kernel calls. This reduces the latencies and eliminates the CPU from having to be involved. By eliminating the CPU, we're reducing context switches between the kernel space and the user, and we're handling the network traffic on the adapter itself. Because RDMA data transfers is performed by the DMA engine on the ROCE NIC, the CPU is not involved in the movement, and thus it frees it up to perform other tasks such as hosting more virtual workloads and other application type needs. Network adapters are generally RDMA NICs is what you need to look for in order to handle RDMA. The ROCE offloads are going to be done in hardware. So there are special NICs that can do this, but there are also software versions of this. So it could be handled with a software version of ROCE. Just a little bit of a note on that. If you are using a soft ROCE version, it's not going to be done on the adapter itself. It will be done on the CPU. So that is going to require more CPU cores to handle the same data transfer. If we do look at RDMA, or I'm sorry, different implementations of RDMA, ROCE is going to be one of the most utilized versions that we're going to see. And we do find this deployed in most of the large data centers. Due to this, it is basically proven, the Web 2.0 data centers have proven that it is a technology that can be used in large web scale environments and useful in speeding up the processes. On this slide here, we take a look at two different versions of ROCE. So there's a version 1 and a version 2. Version 1 requires a lossless network. It is a link layer protocol, and hence it allows the communication between any two hosts in the same Ethernet broadcast domain. ROCE version 2, though, has been expanded to run on UDP or IP, and therefore it can be routable. What we're seeing in ROCE version 1 is it needs to be required to run over a Converged Ethernet, which runs data center bridging. And data center bridging was put together to resolve a lossless environments for FCOE. And it's important to know that ROCE does not use standard IP headers, so it cannot be routed with version 1 through standard IP routers. The Ethernet link layer protocol that requires configuration of the network to be lossless is priority-based flow control, and that's going to be used for the lossless L2 communication. And so we see in ROCE version 2, protocol exists on top of either UDP or IDP. It can be extended across IPv6 as well. And since it's being used in the L2 and L3 communication, it is routable over multiple networks. ROCE v2 adds even greater functionality by changing the packet encapsulation. That's what allows it to be routable over L2 and L3. ROCE has been around for quite some time, and the routability of it version 2 was introduced in 2014. And one point I want to make note of right now is ROCE no longer requires a lossless DCB or PFC fabric, and we'll go into that over the next slide and what all that means. Let's transition there. So DCB is the data center bridging, and that's what was introduced to make Ethernet lossless. And ROCE has built-in error corrections in itself, and it can retransmit so that it doesn't require a lossless network. However, initial implementations recommend that it be configured over a lossless network, and this is how you can get the most performance out of it as well. The most common source of packet loss within a data center is when traffic is just overloaded on ports, such as in an incast situation. So that's why they recommend deploying it with a priority flow control. That will assist in making sure that it's like a traffic cop and it ensures that the traffic is being routed properly. PFC is part of the Ethernet data center bridging. You can see here on the slide, we've got some of the things: data center bridging exchange, explicit change notification, priority flow control, and enhanced transmission selection. We'll go through a couple of these and how they work with either ROCE V1 or V2 in making it lossless. Or we'll also get into, at the end of this slide, resilient ROCE, which doesn't require any PFC or DCB to be enabled, and you can still get a secure lossless environment with some of the latest versions of ROCE right now. So what is PFC? As I mentioned, PFC is part of the Ethernet data center bridging specification. It was originally implemented to support FCOE, which requires a lossless network. It acts like a traffic cop at an intersection, preventing collisions and avoiding packet loss. It basically has to be used with a priority settings, so you need to have several classes. Anything that's going to be latency sensitive, that's going to be running over RDMA, you would mark that as a priority packet, and that would get priority over the less latency sensitive traffic. Priority flow control works very well to provide lossless environments, and it supports is supported by all major switches, or just about all major enterprise switches, and has been successfully deployed in large Web 2.0 networks. However, PFC requires that the network administrators set up VLANs and configure flow control priority settings. These are some things that may be new to network administrators, and due to that, something new oftentimes is perceived as being difficult and perhaps time-consuming, and something that the network administrators may not want to do. So that would be version 1 that would use the priority flow control. There is an alternative mechanism, though, to avoid packet loss, and that leverages the ECN, which is Exchange Congestion Notification. And ECN allows switches to notify a host when congestion is likely to happen, and at the end nodes then adjust their data transmission speeds to prevent the congestion when it occurs. So the ROCE Congestion Mechanism Protocol takes advantage of ECM to avoid congestion and packet loss. And ECM-capable switches detect when a port is getting too busy and marks those packets so that then when they are received, the NIC sees that they are notified that there is a congestion or possible congestion, and in turn it backs off on the sending rate to temporarily prevent congestion from occurring. Once the risk of congestion is removed, the sender then will resume full-speed data transmission. When you're using ECN, that is what you'll probably, if you've heard of resilient ROCE, that is what is known as resilient ROCE, and it's very easy to configure with some of the latest data center switches and ROCE-enabled adapters. You can go ahead and configure ECN very simply. It doesn't have, you don't need to configure any of the virtual LAN environments and settings, and you can get a lossless environment that ROCE has been proven to work very well in. So on the next slide, we'll talk a little bit about wide adoption and support. And you can see a number of vendors here that are supporting ROCE today. As mentioned, it's a very wide support. You can see that it includes OS vendors, hypervisors, virtualization. There's also hyper-converged infrastructures and software-defined storage that are all releasing this. Almost all deployments and demonstrations of RDMA over Ethernet today have been done with ROCE, and many applications have certified ROCE as they recognize the superior performance they can achieve and wider market adoption. As I mentioned at the beginning, as we see the speeds are increasing and computer systems are getting busier and busier, it is recommended that you use a lossless network for that, but it is not necessary. The larger the environment, the more often you'll see that it is designed as a lossless. So it's easy to see why ROCE is being widely adopted, as it addresses extreme I/O needs by providing low latency and high throughput in large computer clusters. And as John mentioned, within Microsoft's SMB, they saw almost twice the performance at half the cost when they used ROCE. We'll see it being deployed in very large use in the Web 2.0 vendors and large cloud computing environments. And most of these applications you see that are using it do have in-box drivers today as well, so make it very easy to support it. I want to go over a few things real quick on ROCE benchmarks. You can see here we've got 3 different benchmarks that we're looking at. One's for ROCE versus TCP. One is the SMB 3.0. Another one is Ceph. And as you take a look at this, you'll really see that it demonstrates the advantages. So in the first test, we had multiple hosts using one ROCE target and another host using TCP IP. Each were sending 64 queue pairs of total throughput, and CPU utilization were measured over time intervals of approximately 130 seconds. In this case, ROCE was running on a network using only congestion management with ECN, so that would be the resilient ROCE, which we spoke about on the last slide. It was not using PFC or a lossless network, and the test demonstrated that ROCE transmits data consistently and closer to line rate and with much lower CPU utilization than on the sender, than TCP. And the next one over, we see a Microsoft SMB 3.0, and this this is the server messaging block. It runs TCP IP, or in this instance, we used a ROCE, it was based on SMB Direct. Both were used on 10 gigabit Ethernet NICs, and you can see that the IOPS performance in TCP IP versus ROCE, there's a much difference in the read and write process. And this demo was used on was based on an online transaction processing workload, and we can see that we get almost twice the CPU usage with TCP IP, while we're getting almost twice the throughput with ROCE. This one again was used on a ROCE v2 instance, which was used in a lossless network, and still we're able to see a good priority or good performance output on that. The final one is based on Ceph, which is a very popular software-defined storage solution for cloud environments and OpenStack. In this test, we can paired I/O writes bandwidth with CPU and CPU utilization. And this one was again a ROCE implementation, and we see here that the performance is anywhere from 30 to 50% higher, and we see that the CPU utilization again much lower. Going on to the next one, I want to talk a little bit about future. And as we saw with we're seeing, I guess, dramatic improvements in sustained bandwidth as we see a change in the storage technology as we go from SATA hard drives, for instance, to NVMe or flash drives and so forth. And we do have, there are other technologies that are going to be coming out in the near future. Intel is talking about 3D XPoint and Optane, which will again move the storage performance up quite a bit. We're expecting it to be over 100 times faster than flash when those release. And all this is having a dramatic effect as we see NVMe SSD drives can provide a sustained bandwidth of about 50 hard disk drives. So as storage gets faster, we're seeing that latency is going to be more and more of a concern. And in the next few years, storage performance will catapult ahead, and RDMA or ROCE is going to be something that is going to be particularly necessary in environments going forward. So as we get faster storage, we're going to see that more and more people are going to start taking advantage of ROCE to exploit the lower latencies, lower CPU usage, and to achieve the faster storage benefits of new storage. Last thing I want to point out is a couple places where you can go to get some additional resources. There is a ROCEinitiative.org, which has a lot of nice collateral on it, good things to go look for it as far as installing, configuring ROCE, different types of test environments. So it's a good resource for you guys if you're looking for more information. They have also partnered with DeMartech. If you guys are familiar with DeMartech, that's Dennis Martin. He does a lot of stuff in the storage industry, and he is also working with the ROCE initiative, has released a ROCE deployment guide. So the latest one was just released several months ago, 2018 edition, and it has many of the popular switches, adapters, and shows you how to configure them all together and set it up for a ROCE deployment. So I'd like to point you guys out there if you need further information on that. And the deployment guide is very useful in helping you set up and figure out what products have been certified, tested, and work with ROCE. At this point now, I'm going to go ahead and hand it over to my colleague Fred, who's going to talk about iWARP.
Thank you, Tim,
Okay.
and we'll get started with Fred. Fred, if you give me just a second, we got a bunch of questions, so let me just try to get one or two of them answered. One was, does ROCE v2 also require PFC? And I think Tim covered that PFC is often used, but it's no longer required. Whether or not you can get good performance without PFC depends on the implementation of ROCE and what type of adapters you're using, but strictly speaking, ROCE has actually never required PFC, so most people doing ROCE v1 were using it. So that's that, and there's some questions about TCP/IP. I think Fred will cover that, and let's go ahead. We'll get to the other questions at the end. Fred, please go ahead.
Okay, thank you, John. This is Fred. I'm with Intel. I'm in the Intel Ethernet Network division. Today I'll talk about iWARP. So first off, I want to clarify one thing. A lot of people think iWARP is Internet Wide Area RDMA Protocol. It's an acronym, but it's not. iWARP actually is iWARP. So I put a link over there so that you can see more detailed information from the FAQ RDMA Consortium website. The reason I'm putting it over there is iWARP actually can be used in a variety of network environments. It's not a wide area network, but also can be used in a local area network, a storage network, and also in data centers. The reason I'm making this kind of statement here is, let's go a little deep into the iWARP. iWARP extension actually was standardized by the IETF in 2007. These are the extensions to TCP/IP stack. So mainly these extensions actually eliminate three major sources of the network overhead: TCP/IP stack processing, memory copies, and application context switch. So if we look at the table here, by offloading the TCP/IP processing from CPU to RDMA-enabled NIC, so-called RNIC, we can eliminate the CPU overhead for the entire network stack processing. Also, iWARP can do the direct data placement to the remote host application memory buffer so that you can reduce the number of the data copies between the buffers. It will save the CPU cycles and also frees up the memory bandwidth. Furthermore, by bypassing the OS and working in the user space, iWARP actually can post a command directly to RNIC without the expensive system calls into the kernel, and you can dramatically reduce the application context switch, CPU overhead, and also reduce the latency. Also, if you want to dig a little bit deeper into the layers of iWARP protocols, you can see iWARP actually is built upon TCP/IP stack. It works on top of TCP. If we zoom in a little bit more, you can see we have three layers of protocol here. The first one is Remote DMA Protocol, RDMA-P. We have DDP, Direct Data Placement over Reliable Transportation. We have MPA, which is Marker PDU Aligned Framing for TCP. Those layers are doing different jobs for iWARP. RDMA-P actually deals with RDMA operations, RDMA read, write, or send. DDP deals with the message segmentation, reassembly, deal with the tagged and untagged memory buffer models, and you can do the in-order message delivery as well. MPA actually can do the framing and add the CRC code. It can insert the marker to show the to identify the start of a PDU and enable the out of order kind of FPDU delivery. A lot of people might think these layers are burdens, additional layers will impact the performance. But on the contrary, actually DDP and MPA, those layers actually enable the ARNIC that can do out of order FPDU delivery if ARNIC can support that, which can help a better performance actually in a congested environment. I think that's the huge advantage of iWARP protocol on top of TCP. Okay. I want to switch the gear a little bit here to talk about the usages, the top tier iWARP applications. When I say top tier, iWARP can be used in a lot of applications. When I say top tier, I mean these are the foundational applications that you can leverage the advantage of iWARP, but upon those applications, you can build up more solution stack to leverage iWARP performance. You can see we have SMB Direct here. Upon SMB Direct, you can have storage spaces direct and Microsoft Storage Replica. And upon storage spaces direct, there could be more kind of complete solution stack over there. Actually, if you want to refer to Microsoft website, iWARP is the recommended RDMA implementation from Microsoft for storage spaces direct implementation. We will also have MEME over Fabric support for iWARP, support both kernel and SPDK. We have ISER, the iSCSI over RDMA extension. UDAPO support. We have OFI, the LibFabric provider for verb interface support. And iWARP also support OpenMPI and Intel MPI library as well. We have MFS over RDMA and also RSocket support as well. Let's take a look at the performance. We talk about what is iWARP, what's inside of iWARP protocol, major applications, but what kind of performance gain you can have compared with the TCP/IP transportation. So here's one example. If you look at the data here, we use an Intel scalable Xeon platform. The latest one actually is featured with Intel Ethernet connection X722 with iWARP support. In this test case, we use a 4x10 gig Intel Ethernet connection X722 and run a SMB Direct data storage performance testing. The workload is a 4K payload with 70% read and 30% write. Compared with the standard TCP, we see almost 1.67x improvement, and we can hit over 1 million IOPS for a single physical host with the 4x10 gig connection. Another example I can give you with iWARP to compare with TCP here is the Cavian FastLink 41,000 NIC. That's a 2x25 gig NIC. You can see this is a test case for the live migration on Windows. There's a comparison between a RDMA, iWARP RDMA accelerated live migration versus a TCP-based live migration. So we have 3 different tests, 2 VMs, 4 VMs, and 6 VMs. Each test we repeat 3 times so that we can see a stable kind of result. You can see the comparison, and with RDMA, iWARP RDMA acceleration, the average live migration time can be reduced by 58% if we compare with the normal TCP. And it's not only a shortened live migration time, but also you can see the more kind of deterministic compared with the TCP-based, live migration. Similarity and differences. John, you want to take a lead? And
Absolutely, Fred. Thank you very much. Let's actually pause and answer a couple of questions. So, Fred, there is a question of, let's see, just a second. Is ICER over iWARP limited to Linux and not available in Windows? Or Fred, do you want me to answer that, or do you want to take that?
As far as I knew, this is only for Linux for now. Maybe in the future it will be available on Windows, but for now it's for Linux only.
Yes, that's my understanding also, that ICER in general, not just ICER and iWARP, but ICER period,
Yeah.
is available in Linux, but and perhaps VMware, but not in Windows. And it doesn't matter whether it's iWARP or ROCE in that case. Fred, there's another question. Is iWARP a lossless or lossy protocol?
So it's a very good question. Actually, if you look at the overall stack, iWARP is built upon TCP, and TCP itself can provide a reliable connection or transportation over a best effort network. So iWARP itself doesn't require DCB to provide a reliable connection. And TCP protocol itself actually can provide the congestion management, the flow control, so that it can run out over the best effort network.
Okay, Fred, thank you. And Tim, a question for you. Can ROCE V2, for ROCE V2, can you use ECN without using PFC?
Yes, that's the whole idea. The ECN is much easier to implement. It doesn't require virtual networks to be configured and so forth. So it's a best effort network, kind of as Fred was saying, to make sure that there's a lossless environment to get the best performance.
Okay, and there's another question that's actually, Tony, I'll put it to you. I guess it's for Tim and Fred. ROCE needs to have converged Ethernet. Does iWARP need it or not? So maybe that could be, Tim, you could first address, does ROCE require converged Ethernet?
Yeah, so converged Ethernet is really the implementing DCB. ECN is a feature set underneath DCB, but you don't need to set up the entire converged network to be lossless. You can just go ahead and configure it for ECN, and that's with the latest switches and adapters. And so you can run it over a run it over a lossless network. It does not require
got it.
DCB.
So you could use either DCB or ECN, but you don't have to use all of the parts of converged Ethernet.
Correct.
Okay, and Fred, same question for iWARP. Does iWARP require converged Ethernet?
Not necessary. You can run iWARP on the normal TCP/IP network. DCB actually helps, but it's not necessary.
Excellent. Okay. And so, wow, we're getting even more great questions coming in here. One is, does RDMA use the TCP, UDP, IP protocol stack? I think I'm going to answer that in just a second, so I'll mark that as answered. And then let's go forward, and we'll take more questions at the end. So thank you, Tim and Fred, for answering that. Let's talk about some of the similarities and differences between ROCE and iWARP. So first of all, they both do RDMA in terms of similarities, and they both support the most popular storage protocols that can use RDMA. So whether if you want to use ICER, which is iSCSI extensions for RDMA, if you want to do NVMe over fabrics, if you want to use SMB direct, all of these can run over either ROCE or iWARP. So that's an important similarity. Actually, both of these tend to use, most of the time, use the same type of verbs interface or APIs. So if you have an application or a protocol OS that writes to these RDMA APIs, usually it can use either ROCE or iWARP. So that's some of the similarities. If we look here at this chart, and it talks about, there was a question that I said I'm going to answer, who uses IP and who uses TCP and who uses UDP? So you can see, well, first for iWARP, it's pretty simple. iWARP, it runs on top of TCP, on top of IP, and iWARP usually has hardware acceleration for both the RDMA and the TCP layers. There was a question about, do you have to have, we'll get more into that later about whether or not you need the TCP offload engine. So again, iWARP always runs over TCP and IP and often has TCP acceleration. ROCE, so actually we go all the way on the far left is InfiniBand. So InfiniBand uses a different physical network. It runs InfiniBand transport over InfiniBand networking over a physical InfiniBand network, but that's not the focus of this webcast. Then we see ROCE v1 and ROCE v2, the difference being that, as Tim had covered, ROCE v1 uses InfiniBand transport over Ethernet. It's layer 2 only, and it does not use IP at all. ROCE v2, which is the majority of ROCE implementations today, does use UDP over IP and then over Ethernet. So after all that description, the short answer to the question is, today, if you look at modern, current implementations, ROCE uses UDP over IP, but not TCP. iWARP uses TCP over IP and usually has TCP hardware acceleration. You see on this chart, many of the vendors are supporting ROCE and iWARP. So a couple of years ago, it was simple. Mellanox was the only vendor supporting ROCE, and Chelsea was the only vendor supporting iWARP, but that's no longer the case. The good news is there are now several vendors supporting each. On the ROCE side, we see Marvell, Broadcom with their adapters, Mellanox adapters, Xilinx with their FPGA, and Kazan, which also has, I guess, either an FPGA or an ASIC or both for their special adapter. And on the iWARP side, we have Marvell, Chelsea, Intel, as Fred outlined. Intel has a chipset which has built-in iWARP Ethernet support, and then Kazan, who does both. So, and then I was going to say we're forgetting Cavium, but Cavium is now part of Marvell. So when we say Marvell here, that typically means like the Cavium QLogic adapters, which can do both iWARP and ROCE. So I think that's answered some of the questions about who uses UDP and TCP. So let's keep going. There's some key differences. So again, underlying network for ROCE is UDP over IP, and for iWARP it's TCP over IP. In terms of congestion management, so ROCE can use DCB or ECN or both, where with iWARP it uses TCP, and TCP does the flow control and congestion management. Now they both offload full direct memory access. So the direct memory access, that zero copy, the bypassing the kernel if you need to, that's done by the hardware for both ROCE and iWARP. In addition, iWARP, depending on the implementation, often offloads the TCP with a TCP offload engine or TOE. Both are routable. And by the way, if I make any mistakes here, Fred and Tim, feel free to jump in and correct me. Both are routable. ROCE v1 is not routable, but again, that's not used so much these days. And in terms of cost, in both cases, an RNIC that can do RDMA, whether it's ROCE, iWARP, or both, usually costs about the same or just slightly more than a regular NIC that cannot. So maybe it's typical that you could get an RNIC for 10% more than a non-RNIC at the same speed, let's say at 25 gig or 40 gig. In addition, I note here that the new Intel platform that Fred mentioned includes 4 10 gig connections with iWARP in there. So that's a way to get iWARP without adding a NIC. In terms of the switch, there was a question about what does the switch have to do, so I'll mark that as answered after I comment that. So for ROCE, traditionally, people have used switches that support DCB, so switches that support PFC or ECN. Today, the PFC is no longer required, though it's still many times used. But if you're using ECN, then you need a switch that supports ECN. You do not necessarily need a switch that supports all the DCB features. But that said, most of the switches today, almost all the data center switches today do support all the DCB features, including PFC and ECN if you want to use them. For iWARP, no special requirement is needed on the switch because it's just TCP traffic. All right, so deep breath. Spent a lot of time talking about that slide. Tim or Fred, before I go on, any comments or any other questions you want to address?
Yeah, I think we'll go over those in the next few slides.
Okay, so let's go on. Tim, do you want to cover this and the key differences about ROCE?
Yeah, so key differences here, as we've mentioned a couple times here, RDMA, when you use ROCE, is a lightweight transport. So basically, the RDMA transfer is going to be done by the adapter with no involvement by the OS or device driver. So it makes it very lightweight, no involvement from the CPU, so you can get the advantages of using the CPU for other applications. And then based on another key difference, just kind of summing up the previous slide, ECN and DCB are necessities if you're running ROCE version 1, and that will provide you with a standard lossless network and with the ability to optimally allocate bandwidth to each protocol on the network. But when you're using ROCE v2 or resilient ROCE, PFC is the only thing that is going to be required for that. It is scalable to thousands of nodes based on just standard Ethernet technologies that are widely used today, and it's well understood by network managers, so it's pretty easy and convenient for them. It's being used and widely deployed by a lot of the Web 2.0, and it's supported by many of the OS vendors and storage manufacturers as well. And as we mentioned, our NIC do demand a slight premium, but are becoming more of a commodity NIC. And I think as we move forward, we also saw that we're seeing wider adoption of ROCE, and we'll see that it's also going to be, premiums for those NICs are coming down and in line with commodity NICs today as well. Fred, do you want to take over the key differences on iWARP?
Yeah, Fred, if you could then cover this slide.
Yes. So we showed earlier on the slide that iWARP is built upon TCP instead of UDP, and TCP actually provides the flow control and the congestion management. DCP is a plus, but not necessarily needed for iWARP. And the key difference here is iWARP can still provide a very high throughput and high performance in a congested environment, even with the TCP only. And there's no specific requirement for the switch. And also, it has a less kind of requirement for the IT professional for the configuration. From the scalability perspective, iWARP is highly scalable. It can scale to tens of thousands of nodes, can span multiple hubs or across multiple data centers. So scalability actually is the key benefit for iWARP for RDMA implementation. Okay.
Okay, great. Fred, anything else before we go on?
Oh, next one.
Okay, use cases. So let's talk about Tim. Please cover use cases for ROCE.
You bet. Yeah, the use cases are wide, very wide with ROCE. We're seeing that almost all deployments and demonstrations of RDMA today are using ROCE. Many of the applications have been tested only with ROCE for RDMA, and recognize that ROCE enjoys superior performance, broader vendor support, and wider market adoption. On the storage side, SSDs and NVMe over Fabric can all enjoy the benefits of ROCE. And if you look at some of these use cases here, cloud computing, we talked about a lot of the large Web 2.0 companies today that are currently using ROCE in very large deployments. These are using a DCB lossless Ethernet environment to make sure that they get the highest performance out of the ROCE implementations. We see that within big data implementations today, ROCE can significantly help performance increase, and so you're looking at time to data can definitely be shortened. In machine learning and AI environments, so that they're tapping on ROCE to lower the inference stages, because AI is a very demanding and of a high network performance. So in those types of implementations as well, you would probably want to use a lossless Ethernet environment. In virtualization, this is something that you could probably just use the priority flow control, kind of a best case effort. And this is VMware, ESX, Windows, Hyper-V, so forth. They're using this to ensure that they see a value in the hypervisor to VM communications, as well as migration of either OSs or storage environments. And a lot of hyper-converged implementations today are using this again so they can see better storage performance. So a lot of use cases in different environments, all of them basically eliminating CPU utilization and achieving a higher performance by eliminating the kernel copies and memory copies. At this point, Fred, I'll go ahead and turn it over to you so you can cover the use cases for iWARP.
All right, we're both trying to move the slides. Tim, let me go ahead and...
Yeah.
Okay.
All right, we got 3 people moving them.
Okay,
so
thank you. Thank you, John.
Stay here on the slide. Fred, please go ahead.
Thank you. iWARP has a lot of use cases here. If you look at the main categories, I want to put them into a few different buckets. High performance computing, iWARP can provide a fairly low latency message passing over an Ethernet network. It doesn't require a specific fabric to run the high performance computing. That's a huge benefit. Also, it's optimized for OpenMPI and Intel MPI, provide very good support for the app-level applications with those message passing interfaces. Storage, iWARP can support both hyperconverged or disaggregated, especially for the TCP-based transportation. iWARP is ideal for the hyperconverged storage so that you can scale in a mixed compute and storage network. It can scale to tens of thousands of nodes and span multiple hubs. TCP can deal with the flow control and the congestion management. That's a huge benefit for iWARP. If you look at the actual applications, the iWARP support is built in the Microsoft SMB Direct. A lot of the storage solutions from Microsoft, like Storage Spaces Direct, Storage Replica, they have iWARP support built in already, and iWARP actually is the recommended RDMA implementation from Microsoft if you go to Microsoft's website to read all those documents. iWARP also support MEO over Fabric, and also the latest persistent memory over Fabric. iWARP also support it. For big data solutions, you can see iWARP can be used to accelerate the Hadoop MapReduce process, Spark shuffling, and Elusio acceleration as well. We have code already upstream in the in the tree for the iWARP support. Virtualization environment, you can see Windows Server Hyper-V got iWARP support built in. VM live migration will show the performance data. You can see with iWARP RDMA, you can accelerate the VM live migration significantly compared with the TCP only transportation. So here are the main use cases for iWARP.
Fred, thank you. So to summarize, looking at obviously iWARP and ROCE both provide great ways to do RDMA and better performance, save your CPU cores when you're going over Ethernet. So in terms of transport, some differences are, we got a typo here, but ROCE uses UDP over IP. iWARP uses TCP over IP. Okay, ROCE traditionally uses a lossless network, though that's no longer, with certain adapters, that's no longer actually required. And iWARP uses pretty much any standard network. So for the adapters, with ROCE, you almost always use an RNIC, though there is a soft ROCE available. With iWARP, you typically use a NIC that supports iWARP, or again, Intel has a CPU platform which has built-in iWARP support. They both do hardware offload, though if you use soft ROCE or soft iWARP, then it's no longer hardware offload, but those implementations are not too common these days because you get the best performance with by using the adapters with the hardware offload. In terms of the switch, ROCE is usually deployed on a switch that supports DCB, though with resilient ROCE, you no longer need all the DCB features. And with iWARP, there's no special requirement on the switch as any standard switch because they all speak TCP. So that said, we do have a bunch of questions, and we'll get to as many as we can. We won't be able to get to them all, but I do want to put in a brief advertisement for SNIA that our next great storage debate is less than a month away, just 3 weeks from now on September 11th. We will have a debate on centralized storage versus distributed storage. So we encourage you to sign up for that. You can register for that on BrightTalk right now. Other great debates that have occurred in the past, and you can watch as a recording on BrightTalk or download the slides from, include FCOE versus iSCSI versus ICER. That one was very popular. Fiber channel versus iSCSI. That was even more popular. And then file versus block versus object storage, which wasn't not as popular as fiber channel versus iSCSI, but also had a lot of viewers. And you can watch all of these on demand, and you can find them on BrightTalk or by going to the SNIA ESF page. We also had a whole series of webcasts called Everything You Want to Know About Storage, but We're Too Proud to Ask. There are 6, I think, of these that cover many, many interesting topics, and you, are encouraged to watch those to learn all sorts of interesting things about storage. We do ask that you rate this webcast afterward and provide us feedback. Tell us know what you think, what was the good and what was the bad. And for those who asked, these slides will be available as a PDF from the SNIA website. In fact, they're probably already uploaded and available now. And in 1 or 2 weeks, we will post a Q&A showing all the questions, especially the ones we couldn't get to live. And you can follow us and find out more about this by following SNIA at SNIA ESF. That said, we do have a bunch of questions left, and we have 5 minutes. So let's try to go quickly on this. Okay, I'm going to answer a few of them myself. Okay, is ROCE limited by the number of hops? The answer is no, not limited by number of hops. However, if the latency gets too high, then you may not get good performance. So it's more a question of total latency across the number of hops, not the total number of hops. It's questions about performance differences. Okay, Fred, here's a question. Do ROCE and iWARP work with bonded NICs? Do you have any comment, Fred, on using bonded NICs with iWARP?
Yeah, iWARP support bonded NIC as well.
Okay, great. And I believe ROCE does also, so that's a good question. There's a question about, does ROCE V2 support long distance or only iWARP? I'll answer that. I think the answer, from a technical standpoint, ROCE doesn't care about distance, but from a practical standpoint, I would say with today's equipment that's available, ROCE V2 is good up to about 40 kilometers. If you have the right kind of switching or switch-to-switch links, you can run ROCE up to about 40 kilometers, and then maybe your performance is not going to be great because of the latency beyond that. And iWARP does not have any limitation on distance, but again, as the distance gets longer and you get more hops, there will be higher latency and the performance will go down. Okay, so for both of you, there's a question, what about NVMe over TCP? So Fred, do you want to take a comment on that first, and then Tim?
It's a very good question. I think the spec of NVMe over TCP is still kind of work in progress. I think we do have a future topic that we will cover maybe end of this year or early next year. I'm doing a little bit of advertisement at this moment. But from Intel perspective, we'll support NVMe over TCP as well.
Tim, you want to add to that?
Yeah, as Fred's saying, we are in development stages right now on a NVMe over TCP presentation, so look for that coming out in the future. And as far as ROCE implementations, yes, we will support NVMe over Fabric or NVMe over TCP.
Great. And I expect that SNIA ESF will have a webcast about this topic towards the end of the year, so stay tuned for that. Okay, is this statement correct? Please clarify, does ROCE V1 support ECN, PFC, but ROCE V2 only requires ECN or PFC? That's basically correct. Actually, ROCE V1, for all practical purposes, requires PFC, and ROCE V2, but not necessarily ECN. ROCE V2 can use ECN or PFC or both. Okay, many questions. What are the performance differences between ROCE and iWARP? Are they roughly the same? Can you guys show us the performance differences? We didn't, SNIA being vendor neutral, we didn't include a direct performance difference, but perhaps Fred and Tim, starting with Fred, do you want to comment on ROCE versus iWARP performance? Fred, you first.
I think we can put that onto the future topic. We don't have a direct comparison between the iWARP and the ROCE at this moment, but it could be a very interesting future topic. We'll bear in mind.
Okay. Tim, any comments?
Yeah, I have seen some of the vendors that we mentioned, both for ROCE and iWARP, do direct comparisons, and it depends on the vendor who's doing it, so it could be a configuration setting on which one's going to have the better performance. So I will just leave it at that for now, but it would be nice to see a more of an apples to apples comparison of the two in the future.
Okay, great. Thank you. There are like 4 questions about that. Okay, I'll answer a question. Can ROCE scale to thousands of Ceph nodes, assuming each node has 36 disks? The answer is that we don't know, but having worked on with the Red Hat and some Ceph people, I would say probably not. We've seen ROCE with Ceph scale to dozens of nodes and work fine. I don't think anyone's tested it, so even the hundreds of nodes level. So dozens of nodes, yes. Thousands of nodes, don't know. Not tested yet. Okay, there's a question about error correction, and if it's too long, we can push this off to the FAQ. Tim and Fred, Tim first. Tim, if you're using ROCE V2 with UDP, how is error correction implemented?
So error correction is going to be implemented through PFC or DCB, depending on which one you've got it configured for. So the ROCE will go ahead and recognize that there's a transmission delay that needs to be implemented, and it will go ahead and slow down the transfers of the information at that point until it receives a go ahead to speed that back up.
Tim, I'm going to be rude and disagree with you there. I think you've just accurately described how congestion management is done with ROCE v2. I'm going to say that for ROCE v2, the error correction is done in the ROCE protocol itself, and I think the question is because it's not using TCP, it can't use TCP error correction, but it's got ROCE error correction running on top of UDP and IP. So I believe that's the answer. But Tim, we can sort that out for the FAQ.
Sure.
Fred,
I think you actually, I think you defined that question or answered that question a little bit better. I misunderstood it.
Okay, Fred, there's a question, and again, we can push it to the FAQ if you think the answer will take too long. What layers in the OSI model would the RDMAP, DDP, and MPA parts of iWARP map to?
Short answer, those three protocols are sitting right on top of the TCP and support the up-level applications. I can put more details into the Q&A document.
Okay, excellent. So we are just about over time. Maybe one last question. We'll start with Fred, and then the other questions we'll have to push to the FAQ. So Fred, are RDMA NICs and TOW NICs the same? What are the differences?
So for the TCP IP offloading, some of the vendor might use TOW to do the complete TCP IP offload. It depends on the NIC vendor's implementation. So different RDMA NIC vendor will have different approach to do the TCP IP offloading. But short answer is TOW is not necessary to implement iWARP RDMA.
Okay, great, Fred. So TOW, which means TCP offload engine, can be used for iWARP RNICs, but is not required, correct?
Yeah. Yes. And there's one quick answer I can give. There's someone asking for the BSD OS support for ROCE and iWARP. I don't know, Tim, if you have any answer for ROCE, but at least for iWARP, from Intel perspective, we support FreeBSD for iWARP.
Great. Yeah, that's a good question. So if you have FreeBSD, I think you have support for both iWARP and ROCE. Okay. I would like to thank both our presenters, Tim and Fred. Excellent job. I thank all the listeners who attended, all the wonderful questions. There are several questions we did not get to, but again, we will do our best to put every question and answer into the FAQ, which we published in 1 to 2 weeks. These slides are available, probably already available online on the SNIA website. If not, they will be shortly, and the recording should be available from Bright Talk within a few minutes after this webcast is completed. So again, thank you very much. Don't forget there are more SNIA webcasts coming up, and there are also recordings of the previous ones. We hope that you'll be able to enjoy more of them if you haven't already. Please do provide a rating and feedback for this webcast. We'd love to hear what you think of how we're doing, and we look forward to seeing you on another SNIA webcast in the near future. So again, Tim, Fred, any last comments?
No. Thank you, John. Thank you, Tim. Thank you all for joining this session.
Yep. Thanks everybody who joined.
Thank you, everyone. This concludes our webcast. And again, thank you for listening, and we hope to see you again soon.